Thank you, everybody. It's great to be here in front of you guys today. And I will be talking today about an extension we've been working on for Typed Racket. And it's something we've tested and would like to tell you about, and we hope to get it to you pretty soon. So it's Practical Dependently Typed Racket. And we feel that this is it's a natural kind of next step in the kind of program specification that you can get by adding Typed Racket to your Racket programs today. And it's maybe one step beyond that. So let's start off by talking about a story. Sorry, We're going to motivate this with a story. So once upon a time, we had a developer. And this developer was sitting down at their computer, and they had a revolutionary game idea come into their head. Now, I know none of you read user agreements, but you've already agreed to not steal this idea from me, so I'm just... So the idea is he's going to pop open Racket, and he's got this little guy that he's going to have on the screen, okay? We're going to have these levels, and we're going to be going around trying to eat these green dots. And while he's running around trying to grab these, there are these nefarious individuals tracking him on the level that he's trying to avoid. So we think this is going to be just absolutely phenomenal. We're going to call it Rackman. And so we've got we start developing, we're starting to create some different modules for the various features and parts of our program. And after a little bit of time, we put this on GitHub and we've got some users, right? Things are going great. Then we start to get some new ideas, some features, right? Maybe some pull requests from some of these people or others, and some ideas and things. So we're really getting some momentum behind this project building, right? And so after a while, we get quite a large user base. So this is turning into a pretty popular idea. Obviously, we can't just leave it as it is now. So we start to add features and make changes to these modules and these things, and even start to add new modules that are going to be interacting with these features. And things are great, but after a while, things get a little bit tumultuous. We start getting bugs creeping up all across the program, and they're quite difficult to keep at bay. They just seem to be creeping up all over the place. And what happened in this particular case was that we kind of built up a little bit of technical debt. We sprinted ahead doing all this awesome development, but maybe we didn't think it out enough. We didn't lay things out. And so maybe we've got some spaghetti code that we need to refactor. Maybe we've got some additional testing that we didn't do. And among all these things that we can be doing to try to fix this problem and get us towards a good, stable game, one thing we probably want to do or want to look into doing is making the specification for these various parts of our program more explicit and actually enforced. And so Racket is there to help us do that, right? We're not on our own doing this. So what are the ways in Racket that we can enforce specifications and invariants? Well, there's a lot of options, as with most things in Racket. So we can do the time-old tradition of just throwing assertions directly in our code, right? So in your thing, unless some invariant is met, we throw an error. We also have Racket's contract system. So if we don't want to be mucking up with all this error checking code, we could take our functions, and as we provide them to other users of our module, we can wrap those in a contract that will be checked on the input and output of these functions. So it's going to be enforcing that specification. And then finally, we also have Typed Racket, which we'd heard a little bit about today, that allows us to add some static compile time specification to our program. So let's talk about a particular part of this game that we're imagining. Maybe there's a render function, okay? And this function takes a vector of sprites and of locations to draw them to the screen, perhaps. And so this is just a really basic, we're looping I, the index variable, from 0 to 1 less than the vector length. And we're going to draw each of those sprites in order. And so we're using Typed Racket, so we want to be statically enforcing some things about this. And so we give it the type that you would kind of expect. Okay, it takes in 2 vectors of the appropriate values, and this one is causing an effect, so its return type is void. And so when we get call sites that are kind of breaking this, that aren't meeting this type when they're calling, they're passing a list there, we get static errors, and this is great, right? We get that immediate reporting. Dr. Racket does a great job of helping you out with these things. But unfortunately, if we have another site where we are passing 2 vectors, but the length of one is not long enough, right? We're not going to draw that third bad guy. That's not going to be caught by the type checker today. And, I mean, obviously there's limits, but that seems pretty simple. We'd like to handle that. And so what we're going to do is take this type of render, and we're going to mess with it a little bit. So we're going to make it a dependent type. So I'm using the squiggly arrow. You see that change there for these. And so we'll kind of shuffle things around. We're going to add an ability to name the arguments so that we can refer to them. And then instead of just any vector of locations, we want a vector of locations that meets some particular refinement. And we're going to throw in a logical proposition. So it's any vector of locations that meets this fact, this logical proposition. Now, a logical proposition, I've never heard of this. Maybe you're thinking you've been using Typed Racket. And so if you were in Dr. Racket and you entered number at the REPL, you would get the type. And what's this funny thing over here? Well, this is a proposition right there. It's telling you if we return a truthy value, a non-false value, the argument was a number. Otherwise, it was not a number. You may have heard these called, and I want you to forget this word the minute I say it, filters. Sometimes people call them those, but they are logical propositions. You can have conjunctions, disjunctions. They're the wonderful things that you can see in other areas as well. And so we'll use the logical proposition that the length of these vectors we have to get is the same as the first argument. So they need to be equal in length. And so if we have this type on it, when we go to have a call site where we're passing two vectors that aren't of the same length, we get a static type error. Now, we have this type, which is giving us a more detailed specification for what's going on with this function. We've pushed a little bit more about what's required into the type. And so with that, can we do anything with the body of this function? Well, there's something that's pretty obvious in situations like this. The vector ref that you see here, this does a dynamic check. So you give it a vector and then you give it an index, and when you go to reach into that, it's testing at runtime to make sure that that's actually a valid index for that vector. In this case, we know that because of the way this is constructed, right, we're in a for loop IS going from 0 to 1 less than, these are all going to be valid. So maybe we're tempted from here, we're going to manually put in these unsafe vector ref calls. These are perhaps analogous to like a C array reference. There's no checking, we just reach into memory and we pull something out. I think that's akin, though, to maybe instead of unsafe vector ref, let's just put little bombs in our program that may or may not go off in the future. And then off to the side, we can have a little stopwatch that we're not allowed to know how much time is left. And then later our program can change and explode, right? So let's not do that. Let's rewind, and instead of unsafe vector ref, we want to use a safe vector ref. Now, what on earth is that, right? Wasn't that the first thing? So safe vector ref, but we're going to take vector ref, which takes vectors of things, an integer, and then it gives you one of those things back, right? And we're going to add some detail to that, just like we did before. So safe vector ref, you have to give it an integer where the refining logical proposition there is that it's greater than or equal to 0 and less than the length of the vector. So that's what we're going to use as the type for safe vector ref. And what is our definition going to look like? Well, we'll just use unsafe vector ref since it's doing the quicker check anyway. But now, with that type, we can statically guarantee the safety of usages of that instead of the waiting for perhaps something to happen bad in the future that we don't know about. And so we have our function here now, and so I've kind of illustrated this through drawing an example. But if we were to just say, what have we added to Typed Racket to do this? Well, we've added dependent function types to the function types that are allowed. So now we can have functions that explicitly name their arguments, just like some of the dependent contracts we saw in Matthias's talk earlier, and then we can talk about those in the types. We've added refinement types, and these are the things that allow a type to have a dependency on some other value like that. And then we've added new propositions. So we already had propositions that things are or are not a type, ands and ors, and we've added linear inequalities over things that are of integer type to that. And then what does this buy us? Well, as we saw, we get more detailed specifications. We can remove safely things like integer bounds checks if we wish. And you can use these same tools in expressiveness. People have shown how to make red-black trees where those static invariants about the data structures because they can all be expressed with the tools that we have, integer relations and things, you can use those as well to make a dependently typed red-black tree. And another nice thing about this extension is we haven't done this in a way where the fact that we're allowing you to have any integer statements like this, it's not like fundamental to this addition. So this addition is amicable to, in the future, if there are additional theories that people would really like to be able to start writing propositions about because it's a decidable, nice tool. We can do that with the way that this is set up. Now, there's this question when we're looking at a extension like this, and that is, we're adding this new expressiveness, but is this going to be a infectious addition? And this was actually a question Matthias asked Stephanie Weyrich, I think at ICFP 2014 or thereabouts. And I thought it was a great question, right? Are we going to get into a situation where we've got a user, and this was the type of render, the original type, and they've got, everything's working fine. Things are type checking, they're calling it on A and B. And then when we go to enrich the type of render, and we give it that more specific type, all of a sudden that doesn't type check anymore, right? We get an error. And maybe it was good. Maybe that was a place in the code where we really weren't sure they were going to be the same length. But maybe it was. We knew they were the same length. But the type checker just wasn't able to figure that out. Well, we can just throw a dynamic check in. Unless these are of equal length, then throw an error. And by adding this, we do get this to type check. So if there are cases like this and you want to add that, that's great. There's a little bit of flexibility there. But if throughout our program we have lots of those little red highlightings going on, and we end up kind of throwing these checks everywhere, that's obviously not a good thing. Our goal isn't to use stronger types and then manually inject that dynamic checking everywhere in our program so that we can satisfy that. So maybe, in some cases it's going to work great, and in others there's going to be a little bit of a give and take, and you're going to be able to decide whether you want that or not. And here, perhaps, we're not ready for that. So the nice thing with this approach is that dynamic check, what we can do, we can get rid of the proposition about them being equal if our program is just struggling to have that be obvious at each usage point. We can go back to the old type. And, that second vector ref there isn't type checking. Well, we can just throw in maybe a error check that we maybe should have had originally anyways to the beginning of this function, and that will type check. And so instead of having that everywhere, we can start out with it here and then, experiment with that. And so the flexibility that this allows to work well with runtime tests, just like Typed Racket does when it's reasoning about the types of values, it kind of allows you to have it your way with how specific you want types to be in different areas. Now, I think another question that's important to ask, the dependent types are kind of a hot topic right now, right? There's a lot of research going in. There's a lot of exciting, awesome systems. And so we've demonstrated a few things here. But is this really dependent types, perhaps you're wondering? Some people, they're very fond of the true Scotsman style of arguments, and they're thinking, well, a true dependently typed language can, and then they've got some satisfying condition here. We can fully type quicksort, or we can type check printf, or we can do theorem proving when we need to. Your program couldn't tell you, but you should be able to get in there and add a theorem proof that that's the case. Those are all awesome things. I'm not ragging on those. But so what we have done, we can't do a lot of those things that I just listed, but we have enabled you to start encoding some of those dependencies in types with this extension. What we've not enabled you to do, though, so this is a little cock example. So this is a definition of quicksort that's actually kind of cool. It takes in a list. It says that it is known to terminate because the length of the recursive calls of the list is going to shrink. And the return value, instead of just being a list, is a list of naturals that is sorted and is actually a permutation of the original thing, right? So you can do some amazing things with dependent types. But the problem, or some of the difficulties that people are still fleshing out in a lot of these cases, is that this particular example, as I was toying around with this in Coq, led to some, it did not type check on its own. It immediately said, okay, well, we've proven some of the obligations, but now we need to start proving these additional things that the type checker itself couldn't prove to be the case. And so at the moment, we're not tackling things like that. We're trying to just have natural extensions that allow additional things to be added without explicit, theorem proving going on as well. This is not Vera Racket, that idea that we heard Matthias talk about that perhaps someday we'll get to see. And so, finally, when can we start using some of these things and experimenting? Well, soon is the non-answer answer. So we have prototyped this extension. So we've taken these ideas and embedded them in the entirety of Typed Racket, and we've confirmed that, with the right design, that this works well with the way that Typed Racket is currently doing things, both in an implementation and in a user sense, we feel. And we've we took this prototype and we ran it on about 57,000 lines of code to see if vector accesses in general, how often we could statically guarantee that they were going to be safe. And we hit about 50% on that mark, and that was without any changes to the code bases. So we've confirmed that it can work well. We have a map for how we're going to add this to Typed Racket laid out. And it would be great. I think a good target to aim for is implemented by this Christmas, 2015. And if not fully implemented, definitely a significant chunk of the steps and features to be there should be there. If you wanted to poke around at some of the details, if you're interested in how Typed Racket is implemented, you can look at what this extension did to get these things to work. And thank you for your time.
Great, that was excellent. If you want to unhook your computer while you're taking questions, we can let the next person get started. And speaking of questions, yes, why don't I give you a microphone? Why don't I do my job properly? Come up here, hand you the microphone.
So that was really cool. There were two decisions you made that surprised me a bit. So one is that when you were giving the dependent function type, it had bindings for all the variables, and then when you had refinement, it had a binding again. So one might expect that you could shortcut that and just do one binding, and that's a low-level issue, but maybe important for practical use.
Absolutely. Yeah. I was trying to keep with the kind of minimal, here's what we're adding and what it gives you, but absolutely in practice there would be some redundancies if we didn't add some additional sugar on top of that, so yeah.
So you're planning on dealing with that, great.
Yes, yes.
And then the other thing is you pointed out quite reasonably, well, we're not doing verification, and it makes sense, of course, to go slowly, but it doesn't seem that hard to just add hooks for that. So why aren't you doing it? What is hard about it? Why is it not worth doing in the first instance?
Well, so we're not doing it in this next semester that has already started where we will be implementing this. But I don't mean to make any claims about in the future it not being done.
But the question is sort of... the question was sort of...
Pull request accepted.
Why is it so actually checking the proofs can be hard, but just having hooks in there that let you put in simple proofs and then allowing more and more complicated ones doesn't seem that hard, but did you leave it out because it is hard in some way that I'm not seeing?
No, I don't have any knowledge that that would be particularly impossible to do, and we've omitted it because of that. We just haven't poked at it yet.
Okay.
Okay, any other questions? I see one up near the front here. He's the master of the NES Chamber Orchestra.
Do you write your own linear inequality solver? And did you require for theory?
We just use a simple implementation of the Fourier-Motzkin elimination method, so we just use our own implementation of a nice, simple, tractable one. So in the future, we could explore other ones or maybe off-the-shelf ones and see if they do a better job, but right now, that's what we're using.
And require for theory?
Not yet.
Okay, I think time for one more question. I don't know if we should take a question from this individual, but I'm a little concerned here.
Did I see that you used yet another syntax for dependent stuff?
I'm trying to not commit to any one particular, so if you
Well,
see
we already have one. Why are you not using the one that exists?
Which one?
ROI.
Well, types don't look like contracts right now.
They do. Assume we cleaned up Sam's mess over the last year. I think we should stick to that. Thank you.
Thank you for that insightful question.